recording. All right, you guys, equilibrium review. When we first learned about reactions in honors chemistry, we always thought like, oh, all of the reactants turn into products, and that means that the reaction is complete. Like we always thought that going to completion meant going all the way from reactants to products, okay? And that's not, in fact, what happens with most reactions, okay? So most reactions go to, ooh, geez, that's not a good start. Most reactions go to equilibrium. And when we say equilibrium, we're talking about a dynamic process. And so really what I'm trying to write here is a definition of dynamic equilibrium. And that is when the rate of the forward reaction equals the rate of the reverse reaction. So it looks like nothing's changing. Like if reactants are turning into products at the same rate that the products are turning into the reactants, it appears to be static. And it appears that the reaction has gone to completion. But that's not really what has happened. What has happened is that you've got collisions happening constantly inside of that container. And so there will be reactions where the products are going backwards and turning back into the reactants. And so we can, we visualize this with that double arrow. So if you've got your reactants turning into products at the same rate that your products are going back and turning into your reactants. And when that is the case and it appears that things are no longer changing, that's when you're at equilibrium. And when you're at equilibrium, you can have a number of different scenarios. You could have more products than reactants at equilibrium. You could have more reactants than products at equilibrium. You could have equal amounts of reactants and products at equilibrium, although that is not the definition of equilibrium. So don't think equilibrium means equal amounts of reactants and products. You know that that's not the case. Remember the paper throwing activity that we did in the hallway? It did not land at 50-50. Like one team was stronger than the other. And we got stuck, I think, at like 60-40. And at that place where you're sort of stuck and nothing is changing anymore, that's equilibrium. And so you can kind of visualize that here on this graph. Move, there we go. This graph right here is showing us two different scenarios. In scenario number one right here on the left, we have more products than reactants at equilibrium. So for the graph on the left, you have more products than reactants when you're at equilibrium. But the reactants are not gone. Like it did not go to zero, right? That would be like, you know, in the paper throwing activity, you know, it never got to the point where all 100 pieces of paper were on the other side of the hallway. It's kind of pretty rare, in fact, that reactions go to completion in that manner. So where did we achieve equilibrium is where this dotted line is here on the graph, where the concentrations of the products and the reactants are no longer changing. It's also possible in this graph here on the right that you achieve equilibrium and you have more reactants than products. And let's imagine what the graph would look like if we happen to have the scenario where reactants and products were the same. It would probably look something like this. Okay, this is where you would have equal amounts of reactants and products. So all three of these are representing different equilibriums, okay? Now, why do we care? You're like, why do we care, Mr. Rivera? I don't care. We do care, we should care. We should care because what if we're trying to make product. Like the product of the particular reaction is what we want to get out of this reaction. Well, if we're trying to make product, but our equilibrium position is going to land us at a place where we're actually going to end up with, here, more reactants than products. Like if this is the equilibrium that I'm going to achieve, that was really crooked. If this is the equilibrium that I'm going to land at, but I'm trying to make products, that's a problem. Like I'm going to need to do something. I'm going to need to shift that equilibrium to get what I want out of the reaction. Okay. So we're going to talk more about that later, about like how we can achieve what we want from these reactions, but that's why it's important to know. Okay. So that's what equilibrium is. Oh, and one more thing, although we're going to talk about this a little bit later, equilibrium can be achieved from either direction. Like think about the dropping of the paper in the hallway. Like I could have dumped all 100 pieces of paper on one side of the hallway or the other side of the hallway. It doesn't matter where you're starting off at. My husband is like, do you need me? Then why are you standing there? He's just like standing there watching me teach. It's so creepy. Okay, you could have started your equilibrium from either side of the reaction. You could have started with all reactants, or you could have started with all products. You could have started with a mix of reactants and products, and you're still gonna land at that same equilibrium position. Now you certainly, let's say you had a reaction that was like A plus C, forward, reverse, making C. Now the reaction can't start on this side and go forward unless you have both reactants A and B. You know what I mean? So you would need both of your reactants, or if you had multiple products, you would need both of your products in order to achieve equilibrium from either direction. But if you start off with a mixture of, you know, all of these, we can predict which way the reaction is going to go. And the way that we make those predictions, the way that we determine whether or not we're going to have more products than reactants or reactants than products, is with our equilibrium constant. And this is our, generically speaking, our equilibrium constant is KEQ. And KEQ is always equal to your products, concentration of your products, all raised to whatever their exponents are, their coefficients, I mean, turns into their exponents, over your reactants, raised to theirs. Okay, so the coefficients in your balanced chemical equation become your exponents. These are your coefficients from your balanced equation. They become your exponents in your equilibrium expression, which is unitless. Isn't that nice? Your small k, rate constants, those have units, but your big K equilibrium constants do not. All right, so these are unitless, products over reactants. What else did I want to say? Oh, okay. We only include aqueous and gaseous species. We do not include solids and liquids, because solids and liquids have concentrations of 1. They're pure, so they're not going to affect your equilibrium. Okay, so we only include aqueous species and gas species that have pressures. This can be written like so in terms of concentrations, like our brackets represent concentrations. If you're doing a KEQ in terms of concentration, we call it a KC. If you were writing this as in all gas phase reaction, and instead of concentrations, you were using pressures, we would use something called KP. It's the same expression, you're just using pressure values. If you were writing out the equilibrium for a weak acid, you would call this thing a Ka. If it was for a weak base, you would call it a Kb. If it was for the autoionization of water, you would call it Kw. And if it was for the dissociation of a salt, it would be Ksp, solubility product constant. So, you know, we did a ton of different types of problems that used all of these different K values. Now this whole thing, so like this guy, the K value is the constant. It is constant at a set temperature. Okay, so the only thing that will change K is temperature. Theo's being funny. That was a good, that's a good joke, Theo. All right. This entire thing, like the whole entire setup, is called the equilibrium expression. So the value is the constant, and the whole entire thing is the expression. Okay. I don't think we need to practice writing equilibrium expressions. Just please remember, you guys, not to include solids and liquids, right? So when you're writing Kas or Kbs for acids and bases, don't include the liquid water. When you're writing KSP for the solubility of a solid, make sure that you, that you don't include the solid in your equilibrium expression. And a lot of the time, we spent so much time doing acid and base stuff, which was always like a 1-to-1-to-1, or just happened to be a 1-to-1-to-1 mole ratio, because we were always working with like monoprotic acids. Oftentimes, you're gonna have these exponents up here. Like, don't forget about the exponents, especially in these KSP expressions. In fact, maybe let's just practice writing one equilibrium constant. Let's write two of them. Yeah, I said we weren't gonna practice, and now I'm practicing. All right, let's practice with like an equation that we're gonna see all the time. It's like a super famous equation, the creation of ammonia. So like H2 gas plus N2 gas making NH3 gas. All right, so we need to balance this. So I need a 2 there, and I need a 3 here. Okay, if I asked you to write the equilibrium expression for this, and it's all gas phase, we would probably be writing a Kp expression. So the Kp would be equal to the pressure of the NH3, my product, raised to the second, over the pressure of the H2 cubed times the pressure of the N2. That's my Kp expression for this reaction. Let's look at how this is going to look different for a KSP. So like, let's say we wanted to know the solubility of the salt calcium chloride. So we would want to dissociate my salt, forward and reverse. Calcium 2 plus aqueous plus 2 chloride ions. Now we're writing a KSP expression, and we're going to be working with concentrations because we're talking about the solubility of ions in solution. So I'm going to put my calcium in brackets, and it is not going to have an exponent. And my chlorine is going to have an exponent of a 2. And it's not going to be over anything. I'm not going to go over my reactant because my reactant is solid. So you can have K expressions with, numerators and denominators, and you can have them with just numerators. Sometimes you could have like 1 over, right? You could have no numerator if your products were solid and liquid, but your reactants were aqueous or gas. So all of those different iterations are possible. Just don't forget those exponents in your KSPs, because oftentimes we sort of forget, these just look a little different than the ones that we do on a regular basis, or the ones we spend all that time doing during acids and bases.
So are KSPs only for aqueous solutions?
Yes.
Okay.
Because it's a measure of how soluble is that salt.
Okay.
Yep.
Thank you.
You're welcome. All right, so why do we care, right? What do these K values tell us? Okay, this goes back up towards the point I was making up here in our graphs. Do we have more products than reactants or more reactants than products? blah, blah, blah. What if you have some aqueous and some gaseous? What is the K then? We would probably call it, well, we would measure them, we would turn our pressures into concentrations, like we would, because the pressure of a gas is proportional to like how many molecules are in there. So we would probably just change it to a concentration of moles over volume. Moles of gas, we would change our pressures to concentrations and do Kc. Yeah, so Theo's asking about like, what if you have, that's called like a heterogeneous equilibria, where you've got like a mix of different states of matter. Okay, so what do these K values tell us? Well, if you have a K that's greater than 1, what does that mean? A K that's greater than 1 means your numerator is bigger than your denominator. So this means you have more products at equilibrium, like this. This would be a K that's greater than 1. If you have a K that's less than 1, it means that you're going to have more reactants at equilibrium. Another fancy way to say this is like products predominate or reactants predominate. So this would be a K that is less than 1. And if you have a K that is equal to 1, it means you have equal amounts at equilibrium. So that's what the magnitude of the K value tells us. And last thing about Ks before we move on to Le Chatelier's principle, or before we move on to Q, is how do we manipulate K values? Like if we had to reverse a reaction, like for Hess's law, if we had to reverse the reaction, we would have to take the inverse of the K value, 1 over KEQ, right? Because now you're talking about reactants turning into products turning into reactants instead of reactants turning into products. Okay, so if you reverse the reaction, you take the inverse. And if you multiply your reaction by a coefficient, you're going to raise your KEQ to that power. And then finally, when you're manipulating your K values, if you were to add up, you know how in Hess's law we add up our delta H's? We do not add up KEQ values, right? So to get a total, like if these were 2 different reactions that we messed with, to get a total, you would not do KEQ number 1 plus KEQ number 2. You would do KEQ number 1 times KEQ number 2 to get the KEQ overall. You multiply them. So your Hess's law manipulations are different than they would be for delta H manipulations. Any questions so far? Excuse me. All right. Well, let's say we're not at equilibrium, right? Like, let's say we just like dumped a bunch of stuff into our reaction vessel and we're like, what's going to happen? Are we going to make more products? Are we going to make more reactants? Is nothing going to happen? Like, how do I know if I'm, or, you dump all your stuff in the reaction vessel and you come back 3 days later and you're like, is this all of the product I'm going to get? How do we know? Well, we have the same exact expression for K, but instead of these being values at equilibrium, like when we plug in these values here, these are the values at equilibrium. At equilibrium. If we're not at equilibrium, if we're at the initial point of the reaction, or if we're partway to equilibrium, or if we don't know if we're at equilibrium, we calculate something called the reaction quotient, Q. So this is the same as the equilibrium expression. It's just values at some point in time. At some point in time. It helps us determine which direction the reaction is going to go. Oh, I think I need a new nib on my pen. It's starting to make ugly noises. Which direction the reaction will proceed to achieve equilibrium? Or it tells us we are at equilibrium. So it's the same expression, right? Q is equal to our products. Oh, this was the lecture we did in Ms. Schmidt's room, remember? Wasn't it? Was it the Q or was it Le Chatelier's? Maybe it was both.
Le Chatelier's, I think.
And everyone was real mature about it. All right, so let's think about what Q means, right? I like to just use this cheat little number line thing so that I don't actually have to think about anything. So I make a little number line like this, and I put my Q's on opposite sides of my K, so I don't have to use my brain. So if my Q is greater than my K value, if this number is too big, how do I make this number smaller, right? I make this number smaller by making more reactants and less products, but that's like using my brain. So instead, this is a cheat method I do like. That's pretty funny because I yell at you guys for cheat methods for other things, and then I use this one. Whatever. If Q is greater than K, the reaction needs to go in reverse, right? The reaction needs to make more reactants and less products to make our Q smaller to get to K. So if Q is greater than K, the reaction goes in reverse or left. And again, it's arbitrary how we decided to write the reaction. And then think about it again. You know, if our Q is too small and it needs to get bigger, then my numerator needs to increase and my denominator needs to decrease, and the reaction needs to go in the forward direction in order to reach equilibrium. So if Q is less than K, the reaction goes forward or to the right to get to equilibrium. And then of course, if Q is equal to K, everybody knows we are at equilibrium. And so nothing will happen. Well, I mean, listen, things are happening, but they're happening at the same rate. So it looks like nothing's happening. Good, you guys, we're halfway there. We're probably more than halfway there. Le Chatelier's principle, are we ready? Is this way too fast? I feel like I would bet my life that whatever 2 questions are gonna be on this wicked short AP test, there's gonna be something about rates and there's gonna be something about equilibrium. Like there has to be. So if you were gonna focus your review, I would really focus. Now listen, of course, everything's gonna include stoic. You know, they might find a way to like bring in enthalpy involved in the reaction. Like you'll see, we'll talk about enthalpy here when we're talking about Le Chatelier's principle. So, you know, but I think like the core of the problem is gonna have to be something around rates and equilibrium. So focus there. And then, you know, thirdly, focus on your thermo. Okay, so Le Chatelier's principle states, this is my favorite chemistry principle, that a reaction at equilibrium wants to remain at equilibrium. And when exposed to a stress, will shift in order to relieve that stress. Right? So you think about it like, you know, you're sitting comfortably on the couch and then your friend is being annoying and like pokes you in the side, you're gonna move, right? You're gonna move away from that stressor. And so like, what are the things that stress out reactions? Okay, so certainly changes in concentration will shift equilibrium, changes in pressure, and changes in temperature. And we're gonna go ahead and just use, let's use that ammonia reaction, 3H2 plus N2 making 2NH3, the Haber process, okay, to talk about what's happening here. All right, so let's say this reaction is at equilibrium and everybody's happy. And all of a sudden, I dump in a bunch more nitrogen into the system. What does the reaction want to do? It wants to use up that nitrogen. So it's going to shift to the right to use up that nitrogen and make more ammonia. Ooh, did I just pick the exact example that I like diagrammed over here? I did. I'm so smart. Look it. Here's a graph, right? Let's say we were at equilibrium. Okay, so like my concentration of N2 was this, and my concentration of NH3 was this, and my concentration of H2 was this. Like this was my initial equilibrium that got achieved. You know, I started off with whatever I started off with, who cares? And I got to that flat line point in the graph, you know, flat line point in the graph being what we were looking at up top. Oh, stop spazzing, mouse. Right? We got to this flatline portion where my concentrations of products and reactants were no longer changing. I was at my equilibrium constant K, whatever those proportions were the happy proportions. And all of a sudden, at that equilibrium point, I dump in a bunch of extra N2. And so it doesn't want all of that extra N2. So what do we see happening, right? Do you guys see how the amount of NH3 goes up? Like I make more NH3 to use up that addition of N2. So I make more NH3. And of course, in the making of more NH3 with that extra nitrogen, I'm also using up some of the H2. So my N2 concentration spikes and then starts to go down as it gets used up. And my H2 starts to go down as it gets used up. And my NH3 goes up. And of course, now I do have different values for nitrogen and ammonia and hydrogen, but the proportion of all of those values is still the same. The proportion of nitrogen to hydrogen to ammonia remains constant because K is a constant. So I can't believe I actually picked the example that I had chosen a graph for. Okay, so if you were being asked, like, well, what would happen to these concentrations as this shift occurred? The NH3 concentration would go up and the H2 concentration would go down as the additional N2 starts to get used up, but these would all come back to equilibrium. The same thing would happen, or a similar type shift would happen if you were to remove concentrations or lower concentrations of things. So like, let's say I removed a bunch of hydrogen from the system. Which way would the reaction go? Well, it was happy with how much hydrogen it had. So if I removed H2 from the system, the reaction would shift left to replace that H2 that I was taking away. So I would start losing NH3 concentration and start making N2 and H2. Hi, what's up? Yeah, of course. So, let's look at one last concentration change, because this is actually what they do in the Haber process to make more ammonia. If I want to drive this reaction forward, if I want to make as much ammonia as possible, I need to remove the product as I make it. If you just take it away, it's going to make more of it. So you just pull out the NH3 as it's being produced, and you can drive all of that hydrogen, all of that nitrogen to completion. Any questions about concentration changes? Okay, let's rewrite that reaction again, you guys. Go ahead and rewrite this reaction here for pressure. 3H2 plus N2. Oh, these are all gases. Sorry, I should have been using states of matter. Forward and reverse 2NH3. Okay. The way that we often get changes in pressure is by changing the volume of the container. Because remember, all of this is happening inside the same reaction vessel. You know, oftentimes we think about like the reactants and products being separated from one another because of those darn arrows in our reaction, but they're not. They're all in the same container. So what would happen if I decreased the volume of this container? Like if I squished down on this container, that would be increasing the pressure inside this vessel. But it was happy with whatever pressure proportions it had. It was happy with whatever the total pressure was. So if I increase pressure, the reaction, I think I want to use yellow for this. The reaction wants to decrease the pressure. How does the reaction decrease the pressure? It shifts to the side with less moles of gas. So in this case, there's fewer moles of gas on the product side. So if it makes more product, you're actually going to get less pressure inside that container because you've got these two diatomic molecules coming together to form a bigger molecule. You've got 4 moles of gas turning into just 2 moles of gas, and the pressure is going to drop. Any questions there? If the reverse were the case, if I increased the volume of the vessel, that in effect would take the pressure and decrease the pressure, but the reaction wants the pressure to be where it was. The reaction wants to increase the pressure, and so it shifts to the side with more moles of gas. In this case, the reaction would shift left. Now, if you have the same moles of gas on both sides, the reaction is, you know, it's out of luck. It's not going to be able to achieve a new equilibrium position. Now, this only happens, you guys, with changes in volume. If you add an inert gas to the system, it's not going to result in a shift. And I'm not going to spend the time going through all of the math on this, although I think we did it after class one day. It's kind of fun math to look at. But when you add an inert gas to this system, you don't get changes. Oh, I always say this backwards. You do get changes, you don't get changes in the partial pressures. I have to do out the math. For those of you that want to do it out at the end, I don't want to say it backwards. It has to do with it has to do with your partial pressures of the gases that are involved in your equilibrium. And because an inert gas is not part of this equilibrium, it's not going to end up changing or needing to change the equilibrium position. So we will, in fact, maybe at the end, do that out to show you guys. There's a fun little diagram we can do. Okay, so it's only when you've got changes in volume. And then lastly is temperature. How does temperature change shift equilibrium? It depends on whether or not your reaction is endothermic or exothermic, so you need to know that. So let's write this reaction out one last time. 3H2 plus N2 making 2NH3. I think when we did the math, it's because the partial pressure stayed the same with the inert gas. Is that what makes sense? Right, if all the partial pressures stay the same, the K value stays the same, or the Q stays the same. You're right, Lindsay. Yeah, thank you. Lindsay's gonna make sure I don't say it backwards. I just decided not to say anything because I thought I would say it backwards. Yeah, I think you're right. All of the partial pressures stay the same when you add an inert gas, but they don't stay the same when you change volume. I think you're right. Thank you, Lindsay. All right, so I think this reaction's exothermic. All right, so if this reaction is exothermic, I'm going to put my heat on the right-hand side of this reaction. Heat is a product in an exothermic reaction. If the reaction was endothermic, heat would be your reactant. So make sure you put the heat on the correct side depending on if your reaction is endo or exothermic. And let's say that the stressor was an increase in heat. Like I heated up my reaction vessel. What would that do? Well, if I add heat and heated up my vessel, it does not want to make more heat. It was happy with however much heat there was. And so this reaction is going to shift to the left to use up that heat. And remember, in this reaction, we're trying to make ammonia. So like increasing heat would be like a bad idea. If I wanted to drive this reaction to completion, I would do this reaction and constantly cool it. You know, this reaction is producing heat. If I were to cool this reaction as it was taking place and I were to remove that heat that it was producing, that's going to help drive the reaction forward because I take away heat, the reaction wants to make heat. So putting this reaction in a cooling vessel would help drive this reaction to completion. And this is the only stressor that's actually going to change the magnitude of your K value. So in addition to shifting, in addition to the shift, the KEQ value changes. So like if it's shifting forward, you're going to be making more products than reactants, and you're going to end up with a new proportion of products to reactants. Your K is going to get bigger. And if it was shifting left, your K was going to get smaller. So you just have to pay attention to what side the heat is on and whether you're adding more heat or removing heat. Any questions on Le Chatelier? Oh, I only have 5 minutes left. It's okay. I just wanted to talk about rice tables for a second. All right, so like how do we do the math regarding all of these reactions? Remember, we use these things called rice tables, where the R stands for your reaction. That's where you're going to write your reaction out. I stands for your initial conditions. These would be your change in conditions. And this is your equilibrium point. So if I was doing a rice table for this ammonia reaction that we've been talking about, we would have 3H2 plus N2 making NH3. This is my reaction. In this particular problem, it looks like I'm starting off with no NH3. So my initial value for my NH3 is 0. And it looks like I've got some N2 and some H2. Now, I don't know how much of each of these I have. I'm just going to put some random values in. So like, clearly I've got the most of the H2. So like, let's say that there's like, I don't know, 10 moles of that, or molarities or pressures or whatever. That's a huge value. They're going to be smaller than that, but like just for fun. And let's say I've got like 7 moles of the N2. If I was doing a rice table with this, I would clearly see that if I'm starting off with all reactants and no products, my minus would be on this side. If I did not know what my change was, I would have to use variables, okay? If I did know what my change was, like if I knew what my equilibrium values were, I could figure out what the change was. So there are types of problems where you know these equilibrium values and problems where you do not know them. So if you do not know them, you use variables. So this would be like a minus 3x. This would be a minus X, right? Because this is a 3-to-1 mole ratio. And this would be a plus 2X. So this would be 10 minus 3X. This would be a 7 minus X. And this would be a 2X. And then you would plug all of this mess into your equilibrium expression, where you would go products. So our 2X squared. Sorry, my phone's ringing. You're not going to have one where the algebra is this yucky. Okay, I promise. I'm just going through the process here. Over your 10 minus 3X, and then you'd have to cube it, times your 7 minus X is equal to whatever your KEQ, KC, or KP expression was. Okay? So like that's the thought process. I promise you'll never have something that gross. But that's how we would do it. Now, if you knew your equilibrium values, you wouldn't have to use variables. But just pay attention, right? That, you know, the coefficients in your equation matter. Depending on what you're starting off with, will determine whether or not your minus X's are on the left or if they're on the right. Like if we had started off with all ammonia and none of these guys, the subtraction would be over here and the addition would be over here. But typically, you know, we think about things starting off going from charging the reaction vessel with reactants and going towards products. So we use these Rice tables and these graphs to help us think about what's really going on at the molecular level. And I think that's all I wanted to do. Yeah. Yeah, last little graph. Okay, so this was just another example, you guys, of if you were starting with only reactants versus if you were starting with only products. Okay, so I know this graph looks really small compared to all of my much bigger graphs. Sorry, you might have to squint. All right, so this graph here on the left is showing starting off with only reactants, like starting off only with the N2 and the H2. If you're starting off only with reactants and no NH3, the reaction has to go forward to get to equilibrium. And if this was the scenario where we were starting off only with the NH3 and with no H2 or N2, the reaction would be going in reverse to get to equilibrium. And if you're starting off with both stuff, reactants and products, that's when you would have to calculate Q to figure out, is the reaction going to go forward or is it going to go in reverse to get to equilibrium. So I just put this here one more time to remind us that reactions can move towards equilibrium from either direction. Depending on initial conditions. And that is all she wrote. Questions? Oh, I should stop recording. Stop recording.